All right, so if you recall with resistors in series, had this we had the equivalent resistance was R equals R1 plus R2 plus R3. And then we said a result of this is that the equivalent resistance is always bigger than the individual resistors. Remember, for resistors in series, that R equals R1 plus R2 plus ... That was for series. Now, what we're dealing with in parallel, they're a little bit different. The equivalent resistance for resistors in parallel is always smaller than the smallest resistor. This works out mathematically, but you can think about it that, if my electricity is coming along and it has a path to take, say you have a single electron, that electron is going to see an equivalent resistance that's smaller than the smallest resistor. Because not only does it have the path that it could take through the smallest resistor, then it has an additional path. So it's like it has, if there's an easier path, it's going to take it. We can also see this mathematically. Let's just work this out. It just works out the way that let's say this circuit right here. Let's just go ahead and find the equivalent resistance, and then we'll address the others. Here, the equivalent resistance for this resistor is 1 over 2 plus 1 over 4. That's 2/4 plus 1/4, that's 3/4. That's 4/3 ohms, or 1.3 ohms. Notice that it is smaller than this resistor, and it's smaller than this resistor. All right, now let's look at this, and we'll actually start to work some of the problems. We want to find the currents and voltages for each resistor, the total current, and the equivalent resistance. I've already found the equivalent resistance. It's right here. I want to find the voltages for each resistor. Well, remember, resistors in parallel have the same voltage. So if I have 10 volts here, that means I have 10 volts here and 10 volts here. All right, so my V1 is going to equal 10 volts, and V2 will also equal 10 volts. Now I can find I1 and I2 because I have two of the components of Ohm's law. That's going to be V1 over R1, which is 10 over 2. Which is 5 amps. And then V2 over R2, which is 10 over 4, which equals 2.5 amps. All right, so that is the currents for each. Now, if I want to find the total current, I can do it this way. I'm going to do it a couple different ways. First, I can apply the junction rule that says that I has to equal I1 plus I2. And so that's going to be 5 plus 2.5 amps, which equals 7.5 amps. Okay, so that's my current, my total current. I can get at that in a different way if I just want to provide a check. This circuit is equivalent to a circuit like this. Let's see, what was our equivalent resistance? The circuit is equivalent to a equivalent resistance of 4/3 ohms with a voltage here of 10 volts. And so if I want to know this current, which should be the same as this current, I just say I equal V over R equivalent. And so that's 10 over 4/3. That's 30 over 4, which is 7.5. So notice here that these two are equal, as they should be, because it's just the total current in the circuit. That's a good, simple problem, but not unlike some that you might see on the test. But you try this quick test. In this circuit, what happens to the voltage in each resistor as you add resistors in parallel? That is, what happens, let's just pick a resistor. What happens to that voltage across that resistor as you add resistors in parallel? This is going to be an important question because our households are laid out in parallel for a particular reason. I want to ask you a question. What happens to the voltage in each resistor as you continue to add more and more and more and more resistors in parallel? Also ask yourself the question, I don't think this isn't in the, it might be in the test, but ask yourself the question, what happens to the current as you add more and more resistors? What happens to the current? That is the total current as you add more and more and more resistors. We will come back to this.